So on this part, on these materials of rotational dynamics, it's very simple. So I would just like to write this equation, whereas the sum of the moments here, it can be written as moments or torque equals to I, which is the moment of inertia, times the angular acceleration. So I think this is all, but today we have to talk about more on the moment of inertia. Because moment of inertia is very hard to find, because sometimes they also ask only about the moment of inertia itself. Sometimes the question only asks the moment of inertia. So basically, in the integral form, in the purest form of moment inertia is r squared dm for all m. So if you have any objects like this, and you have points that a reference point. If you want to take any dm here and have the r, or the distance between those particular dm, and you integrate all over this mass, you get the moment of inertia. Yeah, that's all about moment of inertia. But moment inertia is basically, in a physical way, we can say that we can actually say that this is the thing that define how hard object to be turned um, with respect to your reference point. Okay, so that's all about moment of inertia, but we'll talk more about the example. So one example is that the simple one, we just integrate. Okay, so if you have a long rod, it's not a long rod, it's just a rod with a length of L here. Length is L, and then you rotate this rod around the axis that is in the middle of the rod. What is the moment of inertia? Wait, the mass is M. So to calculate the moment of inertia, we have to integrate all of the mass in this rod with respect to this axis. So if you take the very small mass here, which we can call the M, and it has a length of dx, the mass of dm. So we just use, because this is, we have to inform that this is the long uniform rod. Because this is uniform rod, right? We can say that dm per dx equals to m over l, which is this like a density, but it's like a length density. So if you have half of the mass, half of the length of this mass of this rod, the mass will be half of its actual mass. So it's the same thing. If you have only dx of the x length of the rod, then the mass of this dx part is dm. Then we can just say that dm over dx equals to m over l. This is just like a simple comparison. So we have that dm equals to m over l dx. And then as we can say that the distance between the x to the center is x, we can integrate that the moment of inertia equals to r squared dm. R here is the distance between the points, between the dm to the reference point, which is here is the center. Thus we can just say that this is integrate integral of x squared dm, where dm is m dx over L. But our integration starts from the left point, from the start point until the finish point here, until the final point. The start is with x equals to negative L over 2 until L over 2, because it's the full length of the rod. So the integration here is x squared. Wait, we can take out the m over L because it's constant out of the integral. Integration of x squared dx from negative L over 2 to L over 2. So the moment of inertia is m over L, x to the power of 3 over 3 from negative L over 2 to L over 2, which is m over L, L to the power of 3 over 8 plus by, no, it's negative, L over to the power of 3, yeah, wait, it's 3L here, wait, 3 times 8, so it's m over L to the power of 3, 1 over 24 added by 1 over 24. So it's ml squared over 12, like the final moment of inertia. But usually for this kind of uniform long rod, they already told us that the inertia is ml squared over 12, or maybe somewhat we usually memorize this or remember this part. Okay, so basically for all of the things that we can integrate, this is how you do it. But today, I want to explain more about the concept of this moment of inertia. So, let me think how to explain this. I want to explain about the moment of inertia. But I will moment of inertia in perspective. So this is the concept that usually they don't explain that much, but I want to. So this is a very simple example. So if we say that we have not a rod now, but we have a rectangular mass. This is a mass in rectangular, and we have that one of the side has the length of A and the other side has the length of B. This is actually like a pure rectangular. So if we see the actual form of this is A, this is B, and it has the mass M. But let's just say this is 3D views. 3D views. So let me ask, if we want to rotate this rod in the middle, like with reference of this line. So we rotate this rod around this line. What is the moment of inertia of this rod? Okay, if we want to do this, we can just see the rod in the view of the reference line. So this is the reference line. If we see the rod from this view, okay, from this view, right, we can just see that it's not a rod. It's almost sorry. If we see this rectangular thing with the length of A and B, and we see it from this angle, from this perspective, we can see that it's only a rod with the length of B and the mass M, rotating around this point. So the line will be a point and the rectangular will be a rod. So if we see it from that way, we can just say that B is throughout the line, and then we can just say that the moment of inertia is 1 over 12 mb squared. Why? Because from this perspective, it is only a rod. with the length of b. And if we see it from this perspective, if it's only rotating around this line, and we can say, so it rotating like it would rotate like this. The moment of inertia is only 1/12 of ma squared. Yeah, that's how you see moment of inertia in perspective. Do you guys have any questions? If not, we'll continue to the other concept, which is parallel axis theorem and perpendicular axis theorem. If you guys have any question, you just ask.
Can I ask about dm dx? Why is it dm over dx again? Equals to m over L. Like, why do we even take dm over dx in the first place? Like, why do we take that length density?
Oh, okay, I get your point. Because the thing is that in the moment of inertia, it's integration of r squared dm. But if we have r squared dm integration, we don't have any how to say it? We don't have anything to integrate if it's only r squared dm. It's gonna be like x squared dm, where dm is actually dependent on x. But we don't have the relation, so we relate it from dm over dx. How come it becomes dm over dx equals to m over L? Because it's like a density. So if you have a density, it's mass over volume. So if you have a very small mass and very small volume, it will be the same density because it's uniform. But here, it's only one dimension, so we don't need density. So we just use like the mass over the length is always the same throughout the rod.
All right, thanks. Yeah, understood.
Got it? Okay. So the next thing is that we call this the parallel axis theorem. So in this parallel axis theorem, we have that anything that has the inertia, the moment of inertia. So if we have a thing or any object that has the moment of inertia towards with respect to its center of mass. So this point has to be a center of mass. And we have another point. Either is it inside of this object or outside or any point, it doesn't matter. With respect to this point, let's say this point is, we call this point O. Then the moment of inertia with respect to this point O is the moment of inertia with respect to its center of mass added by the mass of the object times the r squared, where the r here is the distance between the O and the moment of inertia. And one thing to notice is that this only works when you move from center of mass to another point, and you cannot move from any random point to any other random point, or any random point to center of mass. You can move it, but in different terms. But this equation only works if you have the moment of inertia in the center of mass, and if you have the r here, the distance here is the distance between the center of mass and the point that you want to work on. So if we put an example as the rod before, we have the rod with the length L and the mass m with the center of mass here. We'll have the moment of inertia with its center of mass is 1/12 of ml squared. But if we want to rotate this mass in towards its edge, towards its end, we can find the moment of inertia here using the parallel axis theorem, where if we put this as a point O, I equals to I center of mass added by m r squared. R is the distance between the center of mass, here is the center of mass, to point O, okay? So I here equals to half 1/12 of ml squared added by m. R here is the distance between, which is L over 2 squared, which is 1/12. Sorry, why my pen doesn't work? Wait up. Okay, it works now. It's ml squared. It's 1/12 added by 1/4, which is going to be, this can be written as 3/12, or it's gonna be ml squared 4/12, which is 1/3. So the moment of inertia with respect to the end of the rod is 1/3 ml squared. So parallel axis theorem, as I said, it can only be used from the center of mass to another point, and you cannot move from another point to any other random point. So for example, this problem, if you rotate this rod towards this, with respect to these points, the inertia is 1/3 ml squared, and because the rod is symmetrical, if you want to rotate towards this point, it's going to be have the same moment of inertia, which is 1/3 ml squared. But you cannot move from this point to this point, from another random point to another random point. It has to be from the center to another point. So if you try to move 1/3 ml squared added by the m, where the r is L, right? Because if you want to move from here to here, the length is L squared. It's going to be 4/3 ml squared, which is, it's incorrect. So if you want to move O from P, this is moving from O to P, but it doesn't work because you can only move from one point to this, from center of mass to another point, or from one point to center of mass. So for example, if you want to move from point O to back to the point of the center, the equation is gonna be still going to be the same, but the E here, it's the one that 1/3 ml squared equals to ICM added by m L squared over 4. So obviously this is going to be like the same equation, so the ICM will be 1/12. So that's how parallel axis theorem works. Now you guys understand about parallel axis theorem. I want to explain to you about, so this is actually not necessary, but there is a one past year paper problem that uses this idea, and I don't think anyone can. I mean, I'm not sure if anyone can do that because it's very tricky. So, but this is fun. This is fun because you guys join this filtering is for fun. I mean, not for fun, but you guys not taking the course right now, so why not, right? Tricky part. So we use all of this integration to work on this moment of inertia, which is ml squared over 12, as I proved this previously. Now we'll try to do this without the integration, only with the parallel axis theorem, only with the physics. Here, this is the physics. Here's the math. So if we only use the physics, can we do this? Can we prove that the moment of inertia of a rod with respect to its center is 1 over 12 ml squared without using the integral? The answer is yes, we can. How? So let's just wonder that if a rod with the mass m and the length l will have the moment of inertia, let's say alpha ml squared. We don't know the alpha. I mean, we know that the alpha is 1 over 12. But how do we prove alpha is 1 over 12 without using integral? So if we split the rod into two identical rods, how would it be? It would be half of the rod and another half of the rod. But each half will have the mass m over 2 and the length l over 2, right? It's pretty logical, right? So obviously if we have this form of general form of a uniform rod, of course the half of uniform rod can be, of course it is also a uniform rod, right? So half of uniform rod will have E half, which is alpha, with the same form. Its form is the same, it's m over 2, because the mass here is m over 2 for this uniform rod. And the length will be L over 2 squared, right? There's nothing wrong with this. It's still logical, right, for now. And because we have the parallel axis theorem, right, we can move this half uniform rod inertia, because this is the center of mass of the half of uniform rod, into this center of the whole rod, into this point, into this axis. How? We just add by, so the moment of inertia of one of the half uniform rod with respect to the center of the big rod is alpha m over, because this is this is m over 2, the mass, and the length is l over 2 squared. It's gonna be alpha ml squared over 2 times 2 times 2, 8. Okay, sorry, my math is pretty stupid. Over 8. And we added by, because this is the center of mass and this is on a random point, it can move, right? The distance is because L over 4, because this is L over 2. This is L over 2, and this is the half of L over 2, which is L over 4, right? We just add by mass. Its mass is M over 2, right? So the parallel axis theorem is the I center of mass added by its mass times the R, the distance between the center of mass and the new point here. M over 2, and the distance is L over 4 squared, right? And this is for this half with respect to this point, right? But it's gonna be the same for this half. I mean, it's exactly the same. The form will be the same because the mass and the length is the same, and the distance will also be the same, which is 1 over 4. L over 4. Right. So if we multiply this moment of inertia by 2 of this moment inertia, we'll have to have the same moment of inertia with the same whole length rod, which is in our form is alpha ml squared. Is it? Do you guys get it? It's kind of recursive. Alpha ml squared. So if we plug in this value, 2 times alpha ml squared over 8 plus m over 2. Use L squared over 4, so it's L over 4 squared, it's going to be L squared over 16 equals to alpha ml squared. So you can cancel this out. Okay, I'll move this a little bit. Let me resize this a little bit and then continues. It's gonna be alpha ml squared over 4 added by ml squared over 16 equals to alpha ml squared. Because we all have the same ml squared, we can just cancel this out. And alpha over 4, if we move to the other side, it's gonna be negative. So 1 over 16 equals to alpha negative alpha over 4, which is 3 alpha over 4. And do we have this? I'm not sure if we have the same answer. 3 alpha over 4 equals to 1 over 16. It's going to be 1 over 4. So alpha equals to 1 over 3 times 4. Alpha equals to 1 over 12. Right. So we don't need integration to to get the moment of inertia of the rod. As long as you understand that physics allow this parallel axis theorem to happen. You guys get it? You guys have any questions? This is pretty interesting.
No questions.
Okay. So yeah, this is the idea of the tricky moment inertia tricky way of doing moment inertia. So the actual problem of one of the exams, I think it's final exams on what year, I don't know, my friend asked me, is that the actual problem is it is not a rod, but instead it was a cube. It was a cube like this. It was a cube. Yeah. So they asked what is the moment of inertia of this whole cube with respect to the center of this cube if the cube have the mass m and have the side a. I mean, it's pretty interesting that they didn't even teach us any tricky part, like any tricky way of doing moment of inertia like this, and it expect us to do this kind of crazy things. But yeah, whatever. It was fun to do. It I think we should just work on this. So there is two ways of solving this problem, this cube problem. I don't remember what year. Maybe I'll search on this later and show you the actual problem. But this is the problem. Wait. So there's two ways. You can divide the cube to become 8 identical smaller cube. Right. I mean, it's pretty obvious that if you have a cube, you can divide this into 8 identical ones. All right. And you will just say that if the moment of inertia of one cube with a line as the center, a line as the reference line, it's gonna be alpha m a squared. Now we use the mass and the side of the cube. You can use this and you'll find the answer. But it's pretty complicated. Oh wait, and it's not done yet. I haven't drawn it properly. Yeah, it has 8 smaller cubes, which is pretty hard to do because you have 8 things and you have to imagine this in the 3D dimension. It's very hard, right? Now, my other approach is by just seeing this cube from the top of the cube. So I'm combining the tricky way of doing moment of inertia and the way of moment of inertia in perspective so that it's going to be easier for us to work on. How do we do that? Because from the top right, we are just seeing a rectangular thing. It's just a rectangle with the reference with the reference of its center of mass as a point, right? So yeah, we just rotate this rectangle with respect to its center of mass. So we can just divide this rectangle into 4 identical rectangles with each four have the center of its own, and they also have the side of a over 2, because this rectangle has the side of a. So because this is a over 2, right, then this is a over 4. Thus, because this is 45-degree angle, this is a with square root of 2 over 4. Because if a with square root of 2 over 4, sine 45-degree or cos 45-degree, it's gonna be a over 4, right? Why is it not m over 4? Oh, sorry, it's m over 4. Okay, so sorry. Wait. Yeah, it's a mistake. Thank you. Correct. Stupid mistake. Whatever. Sorry, guys. Now, we just assume that one rectangle has the moment of inertia of alpha m a squared, right? And each 1/4 of its rectangle is another rectangle with the moment of inertia of alpha m over 4, with the side is a over 2 squared. So it's gonna be alpha m over 4 a squared over 4, which is alpha m a squared over 16. And if we move this from the center of mass of this 1/4 into the middle, we just added by its mass times the multiplies by the distance squared. The distance is square root 2 over 4. So I is alpha m a squared over 16. This is 1/4 with the center of center of mass, added by its mass, which is m over 4, times the distance, which is a square root 2 over 4. A square root 2 over 4 squared. And it's gonna be alpha m a squared over 16 added by m over 4. It's a times 2 over 16. Which is like this. And then if we multiply this moment of inertia by 4, because we have 4 smaller rectangles here, and it all has the same, they all have the same m over 4, the mass m over 4, the side a over 2, and the distance is also all the same, right? So if we multiply that by 4 of alpha m a squared over 16 added by m over 4 a over 8 has to be equals to alpha m a squared, right? So, oh, it's squared. Okay, and it's 4, and we can also cancel out all of it. So we have a over 4 added by 1 over 8 equals to alpha. Oh, this is alpha over 4. And then we move this alpha over 4 to the other side. So alpha negative alpha over 4, which is 3 alpha over 4 equals to 1 over 8. Thus, we have alpha here is 1 over 6. Oh, sorry. Yeah, it's 1 over 6. So that's how you do that. Any questions?
Why can we use ml square for a square when it's not a rod? Or like why is that equation applicable to this shape? Or like possibly every other shape? Like the alpha ma squared.
Because alpha can be anything. I mean, alpha is just the number that we don't know. So because moment of inertia always depends on the mass and the length or the dimension of the thing, right? So as I said before, as I said earlier, the moment of inertia is how hard objects can be turned with respect to a reference point. So with us having a symmetrical cube or everything, of course the moment of inertia will depends on its shape, right? Its shape by I say its shape is its mass, of course, and the dimension. If we have the same mass but it has the longer dimension, like maybe if we have longer dimension, what do you think is going to happen? The moment inertia will increase. How come? Because it's gonna be it's harder to turn. Oh wait, the moment of inertia is going to decrease because it's easier to turn them if they have a bigger lever or something like that, right? I mean, either it's decrease or increase. Of course, it depends on the dimension, which is in cube. Obviously, the dimension is only the side. There's nothing else in the cube that we can depend on other than sides or the distance between the center with the reference point. But the distance between the center and the any other reference points is just going to be our problem with the parallel axis theorem. So its intrinsic moment of inertia to its center of mass is always going to depend on the mass and the dimension. So in the rod, its dimension is its length. A cube, it's going to be its side. And if it's a sphere, for example, if it's a sphere, it's going to be its radius. Or if it's a cylinder or everything else, it's just going to be its radius also. So yeah, that's how we come up with this general moment of inertia. Yeah, got it.
I think so. Yeah. All right.
So yeah, moment of inertia is pretty harsh. Yeah, I mean it's sometimes regress like this, but most of the time they will just give you the moment of inertia from the start. So if you have a cylinder or if you have cylinder or a plate, oh, my drawing is pretty crap. Sorry. Yeah, whatever. If you have a cylinder with respect to this line, or if you have a plate with respect to its center of mass, the moment of inertia equals to 1/2 of m r squared, where r is the radius. I mean, they will give you this on the exam, but if they don't give you, maybe sometimes you are expected to memorize. I'm not too sure, but I think they always give us this. What else? What are common here? Oh, if you have a sphere, but it's only a shell of the sphere, spherical shell. So it's spherical shell. So it's very thin, and it has the radius r. The moment of inertia is 2/3 of mr squared. If you have a full sphere, the moment of inertia is 2/5 mr squared. Yeah, this is the common shape that they use. Why this is the common shape? Because they can roll. I mean, they can roll, or yeah, anything like that. And if you have a ring, the moment of inertia is going to be mr squared. It's the same as a point. I mean, if you have a point mass, yeah, it's obviously this is r and this is m. point out mass, the I is also mr squared. Because you don't have the m, it's if you just use this equation, a point mass, of course, is going to be, it's not the m, it's m and r squared. That's the only thing that you have. So point mass and ring. Why the ring have the same as the point mass? Because ring is basically just point mass, a collection of point mass together, and then you just add up all of the mass. It's gonna be the ring, so it's gonna be the same, obviously. And I think that's enough for the moment of inertia. And now we'll continue on this rotational dynamics problem. So there are two common types. As I saw from the past year paper, there are only two common types of problem in rotational dynamics, which is the first thing is pulleys. So if you have a pulley that have, so usually in physics problem, they will ignore the pulley mass. If this is the case, then you just don't mind. You just don't bother to see the pulleys as a pulley. I mean, it's just something that connect the threads, and that's it. But if the pulley have mass, if the pulley has a mass, then we have to do a little bit of rotational dynamics here. So I'll just give you a simple example. So the simple example, if we have this pulley, and we have the one side of the pulley is having the mass m1, yeah, it's m1, and this side is having the mass of m2. So, and the pulley has the mass of capital M with the radius r. What is the, let's say, the acceleration of the m2? With the assumption that m2 is bigger than m1. So with this assumption, we can say that m2 is going downwards and m1 is going upwards. And the pulley is rotating this way. Okay. So with this kind of problem, you always have in every dynamics problem, you always have to draw a free body diagram first. And the thing about this kind of problem, with this kind of problem that is involving a pulley with a mass, you always have to have a different tension from each side of the pulley. So you have a thread here, right? This thread will have, let's say, a tension of T2, and this part will have a tension T1. If your pulley doesn't have a mass, if you have a massless pulley, it's the T1 and T2 is going to be the same. Why? Because T1 and T2 is the one that is rotating the pulley. But if your pulley doesn't have any mass, your first equation, your initial equation, sigma moment or sigma torque, is going to be I times alpha. The alpha is going to be there if your pulley is massless, of course, because everything have the acceleration. Then the pulley will also have the angular acceleration, and because the pulley is massless, the I here, the moment of inertia, is going to be zero. If the pulley is massless, let's say the pulley is massless, then the I is zero. The moment of inertia of the pulley is zero. Then the sum of the moment has also to be zero. If you have the zero sum of the moments, then the t here and t here have to be the same, have to equal, right? But not in this case, because the I here is not zero. Okay, so because this is just a plate, a pulley is just a plate or a cylindrical thing, we can say that the moment of inertia is half of mr squared. This is our first equation. Okay, no, this is not a equation. This is just an information. We don't need to write that as a question. So, we just continue this as a free body diagram. This is M1G, this is M2G. Their weight is mass times gravity, and we have to write each particle or each object in a Newton's equation, which is sigma F equals to ma for a point, for a mass, for a thing here. But for this part, it's the sum of the moment equals to I times alpha dengan angular acceleration. Okay, so sigma F equals to ma. Then the F for, let's say, sigma F2, it has M2G negative T2 equals to M2 times A. This is our first equation. And sigma F1 equals to MA. But the acceleration A is going this way. Thus, for the M1, it's going up. If they have the same acceleration, but M1 is going up and M2 is going down. So, sigma F1 is going to be P1 negative M1G equals to M1A. M1, this is M2. This is our second equation. And for our pulley, we have that T2R, which is, I haven't mentioned that the moment or torque is the F times the R, but it has to be perpendicular. The force multiplied by the distance, but both of the force and the R has to be perpendicular. So here, the force is T2, right? And the reference point is the middle. So the distance is obviously the R, and it's the same for T1, it's R also. But because it's rotating clockwise, the moment that is clockwise is positive, and the moment that is anti-clockwise is negative. Why the moment of T2R is positive here? Because it's rotating the pulley clockwise. But T1R here, but the moment from T1, it's negative T1R because it's rotating the pulley anti-clockwise, equals to the moment of inertia times E alpha. The moment of inertia, we should just include this. Okay, so this is the sum of a moment equals to I alpha T2 negative T1R equals to 1 over half of mr squared times the alpha. R we can just cancel out, so T2 negative T1 equals m alpha R, because this is R squared, and this is R, so what's left remaining is R. So before, so this is equation 3, and the last equation is the equation that is connecting the alpha and the A and the acceleration, the angular acceleration and the acceleration. So the I will explain this below. Connection between angular acceleration and linear acceleration. So this comes from the idea that if you have a circle that is rotating this theta to this left, and you have a thread that is connecting it, the distance between this and this, so this is, let's say this is a point A, and now this is a point B. So initially point A is on top, so let's say that initially point A is on top, and point A prime is the point in contact with point A initially. So the distance between A to B and A prime and A to B is equal to the distance between A prime to B. And A prime to B is going to be the length here. The length that is the thread is extending on. So this length is going to be, if you have the R here, the length of BA equals to R times theta in radian. So the theta here is in radian. So this is just a math. If you have this part with the length of theta and the radius of R, the total length from A to B here is R theta, because that's the math in radian. So x equals to R theta. Then we have that if we differentiate x each side with reference to time, d over dt over x equals to d over dt of R theta. It's gonna be x dot added by R theta dot. Dot is, so dx over dt, we can represent that as x dot. This is what I like to write lah. So x dot is the velocity and theta dot is the angular acceleration, omega. And if we also differentiate once again, it's going to be A acceleration equals to R times alpha. Alpha is the angular acceleration. But mind that if the thread is not connected on the edge of this circular thing, you have the R is smaller R. Yeah, just mind that where the thread is connected on, because there are questions that ask if this T1 is not connected on the edge, but it's connected on the inner edge, but T2 is connected on the outer edge. That's another question to talk about. So yeah, because that we have that alpha R equals to R to the expression. So T2 negative T1 equals to half of M. So alpha R here is going to be the same as A. It's going to be A. This is the third equation that we want, third prime we say. So if we just add up all of these equation, add up all equation 1, 2, and 3 prime equations, we're going to have T2 negative T1 equals to half of MA. Wait. T1 negative M1G equals to M1A. And M2G minus T2 equals to M2A. Right. Okay. So if we add all of this up, right? So this is T2 and this is negative T2. It cancels out. Negative T1 is T1. It cancels out. So what's left on the left side is M2G, negative M1G. Because this is M2G and this is negative M1G. And all of this add up is going to be half of M added by, okay, M1 added by M2. Okay, I have to resize this. It's very packed, sorry. It's times A. So the A is M2 negative M1 over half of M added by M1 added by M2 times G. Yeah, this is the expression. You get it? Any question so far? Okay, if not, we just continue again on the second common question. second common question, which is this is a slip and non-slip condition. This is one of the problem that is very hard to explain for me. I mean, it's very hard for me to explain this because we have this kind of tendency that I'll explain it though. So usually we also use this problem with any other kind of circular thing, which is maybe it's a ring or a spherical shell or a sphere or is it a cylindrical thing? I don't know, but mostly it relates to that kind of stuff. So let's just see this from a this is a very general problem. This is not a problem. This is a case study, I'll say, because usually the problem will already tell you in numbers. But in numbers, it's going to be very hard to. I mean, it's gonna be easier to see. But now I'll just try to picture this. I'll help you guys to picture this. So, let's say, this thing, this, let's say this is a cylindrical. This is a cylindrical. This is a plate. Let's say this is a plate, and it falls into the ground. It just falls to the ground, but it has the initial horizontal velocity, which is v naught, and it has the initial angular velocity omega here, omega naught. So it's going to be different if you have a different I would say a different direction of each velocity or each angular velocity. It's very hard to picture, but imagine you have this. Oh, okay. I think cylinder is very hard to imagine. I'll just picture this as a spherical shell, because usually a basketball is a spherical shell. So if if this basketball have the velocity towards the right and it rotates this way before it falls down to the ground. We don't care about how this basketball will bounce back or not, but let's just imagine that this basketball does not bounce back. So maybe this distance here, the height here before it falls down is very small, very small. So the ground will have a coefficient for its friction, right? So the friction will, so this is the tricky part. If you imagine that this ball does not have any angular velocity, of course, when it falls down, the friction will slow down the basketball into going. So the friction is going to be leftwards because it's moving rightwards, right? But if you imagine that there is no velocity here, but it's only angular velocity, so this ball will try to rotate this way, right? So the friction will push the so there's going to be a rotation this way. So the friction will prevent that and give the frictions going to the leftward. So from this case, right? From this case, the friction is going to push to the left. It's going to push the basketball to the left, right? So if you draw the free body diagram, the friction is going to the left, right? And it's pretty simple to imagine. But the thing is that you have a dilemma if it's rotating this way, right? If it's rotating this way, how are you going to take care of this? Because when it's going to the right, when there is no angular velocity, the friction is going to the left. But when there is only angular velocity with no velocity, it's only rotating. It's only rotating before it falls down. The friction is going to the right. So which one do you choose? So the one that you choose is the friction that is the friction. Wait, you have to know which motion is dominant. So if it's dominantly going to the rightwards and the angular velocity is very small, then the friction is going to the left. But if the angular velocity is very big and the velocity is very small, then the friction will go to the right. How do you decide? So to decide which direction of the friction, you have to understand the nature of non-slip condition. Yes, so sorry, this is very hard to picture. So this is like a whole lecture of this, but so your prof will not. So the prof doesn't tell us about anything about this, but they usually come out anyway. I saw these problems like twice or three times from the past year. I thought non-slip is just one formula. Yeah, exactly. This non-slip is one formula, right? But the problem is that it's initially a slip condition, but it will become a non-slip. Okay. So yeah, this is the problem. This is the dilemma because initially it is a non-slip. It is a slip condition, but eventually they'll go to the non-slip condition because the non-slip condition, the condition of non-slip, is the nature of, or I don't know the nature of what. It's just the nature lah. So if you have a thing that is non-slipping that is slipping at first, and it has the form of any circle or any circular form, it will eventually goes to a non-slip condition. Eventually, but at first it will still slipping. At first, yeah. And you have a time before sleeping and the non-sleep condition from the non-natural condition goes into the nature. That's usually the question. How much is the time? How long is the time that it takes from the condition of non-sleep into a sleeping condition? Got it? I mean, it's really hard. So obviously, as I said earlier, if you have this thing rotating, so I'll first explain about what is the non-slip condition. Non-slip, what is non-slip condition? If you have this thing that is rotating, that is moving while rotating. So this thing, if they move, so if you have a non-slip condition, is the condition where you are moving while rotating at the same time seamlessly. What do you mean by seamlessly? If you rotate this way, as I said earlier, this kind of thing is a non-slip. How come? So at first, let's call this point A, A and A prime at the same time. But the moments that it moves to the right, it moves to the right. Okay, sorry. Okay, this is very hard to explain. Okay. So, if it moves to the right, so it will rotate this way, right? So, the A prime will already move up by then, right? Because wait up, if it's move up from to this way, yeah, it moves up to this way, right? So this length have to be the same with this length. Okay. Do you guys get it? And this point B. So the distance between AB here have to be the same with A prime B. So distance here have to be the same with this distance. This is a non-slip condition. It's moving seamlessly. It's like it always touches the ground at all times. It always moving that way. But not that's non-slip condition. There's no slipping. And the type of friction here. There's a type of friction here in this condition is a static friction. Static friction. So static friction is the friction that where the condition is that there is no the static friction. The real definition is that it's the act of non-slip. So if you initially you'll be told that if you have a block that is stationary, there will be a static friction. Yeah, because there is no slip. There is no relative motion between surfaces. So yeah, that the actual definition for non-slip is that no relative motion between surfaces. So the surfaces here is always in contact. There is no relative motion. There's no it always synchronize itself. But if you just imagine, right, this has the velocity v naught and the initial angular velocity omega naught. When it touches the ground at time t0, this thing will still have the velocity of v naught and omega naught. You get it? So yeah, it will not synchronize, because if you want to move this way, of course your omega will have to be clockwise, right? So it's moving together, right, like this. But at first it's going rightwards, but it's moving to this. It's rotating this way. So it's rotating, but it's moving this way. So it's not synchronized. It's just like two motion that is not synchronized, that is not related at all. You get it? So this case, I will tell you, for example, that a case study here. The case is V naught is dominant. Oh yeah, so wait up. I have to write up the for this non-slip condition. You have the relation of this relation. I'll just copy this one. Wait up. I'll just copy this all of this. Copy this condition. This is the non-slip condition. X equals to r theta or whatever. Yeah, this is the condition of non-slip. Okay. So that V naught is dominant. I say V naught is dominant. So if I say that V naught is dominant, it will eventually goes into non-slip condition that is moving to the right. Okay? Because why? Because if the V naught is dominant, the friction will counteract the V naught. If it counteracts the V naught here, if it counteracts the V naught F is here, it will rotate the F here will become a moment that will rotate this motion from going this way, from going anti-clockwise to a clockwise condition eventually. So because V naught is dominant, okay, the friction F is going, so the free body diagram is going to be like this. And for this is the non-slip condition, yeah. And one thing to take note is that if you have a sleeping condition, you'll have the friction here, the type of friction is the kinetical friction. Kinetic friction. So, before I do this, I'll give you some imagination to imagine. I'll give you the concept to imagine. So because the V naught is dominant, the friction is going to turn out this way. Of course, they will eventually reach a non-slip condition to the right. The non-slip condition is the motion to the right because the V naught is dominant. So they will move to the right. And because they will move to the right, eventually they will get to a point where the V equals to omega r, which is a non-slip condition. So because the V naught here, there's a friction here. The friction here is going to reduce this V naught. If they reduce the V naught is going to be like this. Okay. And the friction here will rotate this omega naught. Okay. Will change this omega naught into this direction. How? Because at first it is rotating this way. As time goes on, it will reduce until 0, until there is no angular velocity, and the angular velocity will be rotated because there will be still f by then. It will be rotated into the other direction, to clockwise direction. Do you get it? I don't know. If you can you imagine that this is very hard. This is very hard to imagine. If you have the omega naught here is small, right? If you rotate, so how to imagine? How to imagine that? If you throw a ball but rotate the ball inwards into your body, so like this, you throw the ball to the front of your body, like it's going away from your body, but you rotate it inwards to your body. But the ball doesn't bounce. So you just imagine you have a bowling ball, but you rotate it inside of your body, but you throw it away from your body. But the way you're throwing it is that you're throwing away with the bigger effort than the way you rotate it. You get it? Okay, it's very hard to imagine. Whatever. Yeah. So you eventually have to reach this condition. So because it's V naught here, it's omega here. You have to turn this omega into this way, but you reduce the V here to this way until it reaches this condition. So yeah, this is the F, because this is mg, this is n, the normal force from the ground, and n equals to mg, and F, because the non-slip condition, the slip condition will have the kinetical friction, which in kinetic friction the formula is mu and multiplied by n. It's supposed to be mu k. Let's say the information here is mu k. So mu k times mg, it's mu k mg. This is the Fk. So sigma force equals to ma, because the acceleration is going to this way. So because the force is going to the left, it's negative mu k mg equals to ma. So the acceleration is negative mu kg, where why acceleration is negative, because it's going to the left and our motion is to the right. And for the moment, sigma moment equals to I times alpha, where the I here is half of m r squared to the alpha, and moments here is rotating clockwise, which I'll say just a positive moment, which is F times R. With respect to this center point, it's FR. So we'll have alpha equals to 2F over MR. Okay, I'll say that this is the second equation and this is the first equation. So with this initial condition, we'll have that V naught. This is the basic kinematics that I was telling you. That I made the video on as the first video. This is a simple equation. So V equals to V naught times AT. V equals to V naught. The A is minus mu K G times T. This is our third equation. And for this is going to be the same with the angular motion, but it just change it to angular. Omega equals to omega naught added by alpha T. But the omega here, we consider that the clockwise motion is positive. So because initially it's anti-clockwise, it's negative. So omega equals to negative omega naught added by 2F over mr times T. This is fourth equation. So to reach the final non-slip condition, it has to be V equals to omega R. So the V here is V naught negative mu K G T equals to omega R, where the omega is negative omega naught added by 2F over mr times T times R. Why? Because it's V equals omega R, right? This is the V. Final condition has to be non-slip. V equals to omega R. V equals to this omega times R. So V naught minus mu K G T equals to negative omega naught R times 2F over MT. The F here is mu K mg. So the M can be cancelled out. So V naught added by omega naught 0 R equals to mu kgt added by 2 mu kgt. Mu kgt. This is not mu g, mu k. So it's going to be 3 mu kgt equals to V naught added by omega naught R. So T equals to V naught added by omega naught R over 3 mu kg. So this is the time that it takes from the slip condition into non-slip condition. Yeah. Get it? It's very hard to understand. So how do you know? So I mean, it's pretty obvious. What I mean would be sorry, not pretty obvious. So it's not obvious where the direction of the friction force is going to. But if you got it wrong, the A here is going to be plus. Okay. So let's just imagine that we switch all of this. So V equals to V naught added by mu kgt. Let's say the friction is wrong to different direction. It's wrong. And the omega here equals to negative omega naught negative 2 F over mRT. Let's just say that everything we just switch the direction because we have the wrong friction. So omega equals to negative omega naught negative 2 mg mu over mr. M just do it this way. And then if we do the same relation, I'll just do it for you guys. V naught plus omega naught r. I do this in my head. Wait. Equals to negative 3g mu k t. Yeah. Wait. Let me think. Yeah. I think it's this way, right? So you have the t equals to v naught plus omega naught r over negative 3g mu. You know that g is always positive, mu is always positive, v naught is always positive, and I mean v naught and omega naught is the one that is known from the problem, because the problem is also always say that the problem will not tell you that the velocity is negative something. I mean the velocity is going to the rightwards with this much. So v naught and omega naught is just a magnitude, so it's positive, right? R is positive. So everything here is positive beside this negative value. So we can just say that it's negative v naught plus omega naught 0 over 3g mu. Okay. Well, we have a time negative. You cannot go back to the past. I mean, you don't have a negative time. So this will be happening if you choose the wrong direction of the friction. So so this is not a trick, but this is the thing, because it's very hard to consider if it's at first is it either sleeping or not sleeping. If you're very desperate, at the end of your finals, you found this kind of problem, I would advise you. So this is my advice: is just to do it, and just randomly choose any direction of force, of the friction force, and then you got it wrong. Okay, you got it wrong because I mean you I said you got it wrong is that you got the negative value of time, and then you just change it into another direction. Okay, let me check. Can define leftwards positive or rightwards positive, etc. Yeah, you can. You can do it anytime. I mean, however you would like to do it, whatever. But if you got the time in negative value, you just switch the force. You just switch the direction of the force, and then you're done. Then you're done with it. Yeah, that's my advice. Got it? Okay, so that's two common questions regarding rotational dynamics. So this is all of the rotational dynamics. Any other kind of problem, you guys can ask me about it. But yeah, usually this is the two common problems are pulleys and slip and non-slip. Slip and non-slip, I find it several times only, 2 or 3 times. But pulleys, I found this many times. I mean, it's not always in forms of pulleys. I guess I found a time where it's not pulleys, but it's like a globe. I don't know what it's like, a miniature of a globe, but it has a thread rotating it, and it's moving. Yeah, it's basically a pulley if you see from top. I mean, yeah, but I don't got the bullet hit and the block turn. Okay, we'll go we'll go through that after this, because that's the problem where you have a hitting things. If things hit another thing and stuff, that's not a rotational dynamics, but it's angular momentum problems. And then that's also my plan to explain about that. So this is angular. So I mean, yeah, actually, angular momentum is technically part of rotational dynamics, but I would say that rotational dynamics is the one that involves external forces or external moments. So angular momentum, we usually say that it's L equals to E, the moment of inertia, times the omega, or if it's okay, wait if it's a point mass, if it's a point mass, it's M times phi r, where the phi and the r is always perpendicular. Okay, this is the angular momentum. This is another part. Yeah. So for this angular momentum, you usually consider a problem with the conserved angular momentum. So conserve angular momentum. So if you have how do you consider a system with the conserved angular momentum? Usually, if you have a problem, you will if you have a problem with rotating stuff, it will be very hard for you to understand if it's either the angular momentum that conserve, or is it the momentum, or is it the energy or stuff. But to consider it, you have to understand that as long as there is no external moments, or what I would say that the sum of the moments or sum of the torque has to equals to 0, then the angular momentum conserve. Another thing that you can choose a point, a reference point. Which the angular momentum conserve. Okay, and this is actually all about angular momentum. Oh wait, as as I have been saying for the parallel axis theorem, it works similarly with the angular momentum. So if you have an unsynchronized motion, by I mean unsynchronous motion is mostly sleeping condition. So it's sleeping condition. So it's not a non-slip condition. You have that the angular momentum is the angular momentum towards its center of mass with reference to center of mass added by the angular momentum of a point mass What do I mean by this point mass is that if you have this thing rotating with the velocity of v, it has the mass v, m, and v, and it has its angular momentum to its center of mass. For example, if it's rotating, then you guys can add the angular momentum as the angular momentum with reference to its center of mass, and assume this this object as a point mass and added by the angular momentum of that point mass. So, for example, this thing rotating with the angle so let's just say that we have a rectangle that is rotating to its center of mass with omega, with the angular velocity omega, and it has the velocity v here, and it has the distance, the perpendicular distance r. The angular momentum is, let's say this is a, the ma squared times omega added by, so this is the angular momentum with respect to its center of mass, because the moment of inertia of a rectangle is 1/6 ma squared times omega. So it's e omega, I times omega, the angular momentum with with respect to its center of mass added by the angular momentum with a angular momentum of a point mass. A point mass is this mass. We just assume that the center of mass as a point mass with respect to the point that we want to know, where the angular momentum is mvr, right? Where the v and r for a point mass is always perpendicular, have to be perpendicular. If it's not perpendicular, you made it perpendicular. So the v here is already perpendicular with r, so you just add it by m v r. Okay, because the v and r here is perpendicular. But for example, if it's not perpendicular, let's just say that you are given that this length is L, not L. L is the little L, and there's an angle theta here. The R and the V is perpendicular when the R is L sine theta. So R can be L sine theta here. Okay. Okay. This is the theory of angular momentum. And after this, we will try one of the problems. Okay. Let me see your description. Cut the bullet, hit the block, and the block turn. Which problem is this? I don't remember, but I'll try to search for this problem. Wait. I think I remember the question. Is this the questions? If I'm not mistaken, this is the questions that you're referring to. So this is because I think it's the questions, the continuation of this problem, is it? Because this problem, this kind of problem have the part B where this 3D cube hit by a bullet, if I'm not mistaken, yeah. So there's a bullet here that is shooting from afar. Okay, with the velocity v, and I think this is pin. There's a pin here, so it can only rotate with respect to this pin. Is it? I think this is a problem. And then there's this block have the mass m, and the smaller particle here have this mass m, smaller m. And there was an okay, let's just let me think. Let's just don't mind those assumptions, because those assumptions is just to reduce the math. But I think it's okay if we have a lot of math anyway. I think that one my exam. Oh, okay, nice. Wait, you're not in year one? I think it's not in my exam. This is, I don't. Oh, okay. Then this is your okay. Then this is your problem. Okay. At that year, I think, if I'm not mistaken, you have that this mass m is so much less than this mass big r. If I'm not mistaken, yeah. But this is just to reduce the math, because I'm not doing the math, right? I mean, I use this all in variables. I would just use the the variables. I don't mind disregarding this. And it's embedded into the. Oh yeah, the problem is that if we don't, if we if we don't regard this, we have to know how deep this particle embedded in this block lah. Yeah, we'll use this. Sorry. Okay, m is so much less than m, because okay, I'll explain why. So the thing is that if we, let's say we have the center of mass of this block here, of this cube here, it's here, right? So as I said earlier, to understand, to do the angular momentum problem, you have to check that the sum of the moments is 0. Okay, so we cannot use this point as a reference point. Why? Because when it hit by a bullet, when the blocks hit by a bullet, there will be force here and there. There will be force that is acting against the bullet, and the bullet is giving the force to the to this the blocks giving the force to the bullets, and the bullet is giving the force to the block. And it is because it's force. According to Newton's third law, it's going to be the same because it's internal force. It's internal force. Bullet give the force to the block. Block give back the bullets. It's the same. This is internal force. Internal force. And this internal force does not cause internal does not cause external moments, because you just get it, right? Because this times the r here added by this times the r here, because the r is the same and the force is the same, you have the moments that is balancing one another. But the thing is that if bullets hits this block, these points will give back force, because there's a pin here, right? The pin is holding the blocks so that the block is not moving. Get it right? Oh wait, what's it? Yeah. The pins here is holding back the block so that it's not moving. So right, there will be force. Wait. I think I got this. Oh yeah, this is the exact same problem, but I changed this into a pin. Why? Because I'm not sure, but I think in the problem, right? In the actual problem, this is a ground, but the friction on the ground is infinite. So I think this is about, if the ground has the infinite friction, what does it do? It does that it means that it cannot be slided. It cannot move. It cannot translate. It can only rotate. So it has to be raised up by some degree, I think, if I'm not mistaken. It has to be rotated anyway. So it's the same thing if we change this into the pin. But if it's on the ground, so the force is going to be the friction force here, which is infinite. So you cannot calculate, right? So you cannot choose this as your reference point. But you choose this point. Let's say this point is O. If this point is O, you can choose this as the reference point where the angular momentum conserved. Why? Because there is an internal force here, which causes an internal moment, which doesn't matter. But the force here has an arm length of 0, because the moment is force times the length, right? That is perpendicular to it. But if your force is here, the length is 0, because the force is exactly at the point. Okay, so we just use this as a reference point. Reference point. I'm very sorry to explain this a very long time to only explain this, but it's important for the concept, and you guys are not here for the exam, it's for the concept, right? Because it's fun. So I think the questions told us that you have this length of L and the side is A, right? So the initial angular momentum is only from the particle, because at first this block is not moving, this cube is not moving. So the conservation of momentum, of course, that initial momentum is equals to final moment angular momentum, which is at first it's mvl. V and L is already perpendicular here. V is going this and L is this, and it's perpendicular, no problem. And because it's embedded, it will become one object, right? One object with the new moment of inertia, because now this mass m is part of the moment of inertia, right? So let's say that it's embedded this deep of d, right? So you have this length L, and this length is a minus d, because because the length of the and it's embedded by d, so it's a minus d here. Between this with the reference point is a minus d squared added by L squared. So it's m. So the new moment of inertia, because the moment of inertia, okay, the moment of inertia we have to find first, because the moment of inertia here is 1/6 of ma squared, but it's with respect to the center, right? So can we use the parallaxis theorem here? Yes, because it's center of mass, and we want to move it any other point to this point where the distance here, because it's a, and this is a over 2, and this is a over 2 square root 2, right? This a over 2, and this is 45 degree, right? So it's added. So this length of, let's say, this blue line here, r is a over 2 over 2, right? Or a squared 2 over 2, added by the mass m times a squared 2 over 2 squared, so ma squared added by ma squared times 2 over 4, it's half, then it's 4 over 6, is it? Because it's times 3 times 3. Yeah, it's 4 over 6, it's 2 over 3 ma squared, the moment of inertia. So the moment of inertia with respect to point O is the moment of inertia of the block, which is 2 over 3 ma squared added by the moment of inertia of the points here, whereas it's m times r squared. R is L squared over the r here, it's new r. Let's do it on orange. R, where r squared equals to L squared added by a minus d squared. So it's m times r squared, which is L squared added by a minus d squared. Oh, we use r for this. We just change this into r prime. Same thing. Times omega. Why? Because the bullet now and this the embedded bullet now and the block is now moving with the same angular velocity. That's why the problem here, I think the problem mentioned this. Why do they mention this? Because if they do not mention that, we'll have to deal with this, and they didn't even give us the depth of how much the bullet is going, how much of the depth of the penetration of this bullet, which is why they have this. Why they have this? So because the m is very, very small, right? The m here is very, very small. It contributes very little to the moment of inertia after the collision. So this part is very small compared to this. Right? So we just ignore this. So mcl, so equals to 2 over ma squared omega. Yeah, that's how it goes. So after that, you have an omega of 3 mcl over 2 ma squared, and that's how you do it. That's the omega. But I think the question was not asking about the omega. The question was asking about how much. Wait. How how much what the initial velocity v has to be so that the block can turn can turn a full turn. No, it's not a full turn. So at least the block. So I think I remember reading the question was telling us so that the block from this position it can rotate to this position. So it will reach to the top first, and then it goes to this position. Yeah, that was the question. Because after it's just gonna be energy. Okay. Yeah, this is the question. So how to do it? So this is a common problem in physics. So if you have this kind of position, to reach this position back, you have to at least reach the peak lah. The peak is where the block have the most energy on. So to reach those energy, just imagine at the peak it has no velocity, but at least at the peak here they have velocity, so that it can still move, right? It has to be to have the angular velocity here. Okay, it's pretty easy. We just assume that at first, so with the conservation of energy, the initial energy here is half of I omega squared added by mgh. The h here is for this block is a over 2, but for this embedded bullet is L. But yeah, we already know that m is very small, so it's only for the block. Half of the I here is 2/3 mr squared omega squared plus m, which is the mass of the block, times g times the h here is a over 2. At the top, right? At the top, you have to reach the top here. Here it's the length of this, which is a over 2 with the square of 2. Yeah, which already there. So the final energy has to be the same. Energy at top, yeah, at the top position where you have to reach first. So at least you have to reach this position so that you can continue turning, right, to this position. It's gonna be at top. It's going to be the energy, the kinetical energy added by m g. It's why a over a is a over 2. Okay, sorry. A with square root of 2 over 2. So it has to be the same. We just equate these two. Okay, just copy this. Copy equals to this. Copy. So at least they have a velocity on top, right? So the kinetic energy here has to be bigger than 0. Otherwise, it's gonna be, if it's 0, it's just going to go up to the top and then it stops there. I mean, in reality, it won't stop because there will be wind or stuff or things to let it fall because it's unstable. But in physics, yeah, if the KE is exactly 0 at the top, yeah, it will stop because there's no wind, no friction in the physics problem. I mean, in this problem now. But in reality, it will either go back to this or goes to there. Yeah, so it's at least bigger than 0. 0.00 something will do. Okay. So the KE equals to we just continue 1/3 mr squared. This is 1/3 mr squared, right? Because 2 cancel out. Omega squared added by mg a over 2 negative mg a squared of 2 over 2. Yeah, right? We just move this to the side, right? And the omega here depends on the v. And then the KE here has to be bigger than 0. KE has to be bigger than 0. This is KE, the kinetical energy. Thus, this has to be bigger than 0. This is our inequalities. The omega we just plug in from this, right? This is the omega. We find the omega already. Oh, why did I delete it? Oh crap. Okay, sorry. 3mvl over 2ma squared. Okay, whatever. Just copy this now. Base squared. 1/3 of mr squared has to be bigger. Wait, added by mga over 2 negative mga squared of 2 over 2 has to be bigger than 0. It's g, it's not a. Okay, so we move this into the other side. Okay, it's 1/3 of mr squared. It's 3 squared m squared 3 squared l squared over 2 squared m squared a to the power of 4 is bigger than. We move this to the other side. We get that it's mga over 2 squared of 2 negative 1. And then we just cancel out some of the terms here so that it's easier for us to work on. Why we have r here? What is r? What did I do with r? The moment of inertia is not r. Oh, it's a. Why it was r? Here, the moment of inertia is what 2/3 of ma squared. I wrote it as r. Why? Sorry, a lot of mistakes. It's a. It's a squared. It's a squared. So a squared. Okay. So yeah, it's a squared a to the power of 4. It's a squared. We continue on this page, yeah. It's m squared 3 squared l squared over, oh, it's 3 because it's 3 to the power of 2 and the 3. Okay, over 4 m a squared to be bigger than mga over 2 square of 2 negative 1. So the velocity squared here has to be bigger than, oh, you can cancel it out, so this becomes 2 m squared ga to the power of 3 divided by 3m squared l squared square root of 2 negative 1. And so obviously v have to be bigger than the square of this. So the square of this we can, because all of this, there's m squared mm, we can also make it m over m. A to the power of 3 over l to the power of 2 m a over l, square root of 2 g a over 3 square root of 2 negative 1. I am sure that this question had to have, I mean, it has to have the number, but for now it's just the variable here. It's the same, I guess. Wait, the dimension is correct. Yeah, it's correct. So yeah, this is how you do that kind of question. You choose which point as a reference point where the sum of the moment is 0. If the sum of the moment is 0, then you have that the angular momentum is conserved. As the angular momentum is conserved, you just first do the angular momentum conservation. Whereas it is the what is it called again? It is the collision point. It's only on the collision time. After the collision, you conserve the energy. The common mistake is that when you are conserving energy from the start. Why? Because the conservation of energy does not work if it's if you have a collision point where it is embedded, when it's embedded, there are some energy loss goes into the friction here when it's embedded here to the friction. So yeah, obviously the energy does not conserve every time. It at first the things that is conserved is the angular momentum with respect to reference point. After that, we have a one object with the angular velocity like this, and after that it will have to go through the angle to the conservation of energy, because after the collision there is no other um there's no other friction or stuff. Yeah, that's how you do this kind of problem. Mostly on the collision part, mostly on every collision problem, you have to do the collision first and then the conservation of energy. It is also a common mistake to conserving the energy from the start. You cannot conserve this mv half of mv squared energy here. It's incorrect. Yeah. Any questions? It's a long question. It's a long problem. If you have any other question to be raised on, yeah, we can talk about it. Any past year paper that intrigues you guys? Yeah. Okay. What time is this? It's 3:11. When did we start? We start at 1, right? Oh, it's 2 hours already. Okay. So I think it's gonna be very long if we don't end this now. What did I cover? I did cover about angular momentum and rotational dynamics. So it's good to go. What I haven't covered for the mechanics is the other. So before we end, I want to highlight about this this these things regarding collision that is very interesting, that I like the most about that. I mean that I always like to use in every kind of collision. That is not embedded lah. That is not so. In collision, right? In collision, sometimes you will have a problem where the where it's elastic or it's fully inelastic. Fully inelastic. What I mean by fully inelastic, that it moves together afterward. It moves together after the collision. Like this kind of like the exact previous question that we did before, it's embedded. It's moving together afterwards. Or if you have a block and it moves with the velocity v and this is stationary, and then they move together afterwards with the same velocity, it's fully inelastic. Or you have a somewhat inelastic or inelastic. It's just inelastic, but it's just that the energy doesn't conserve, but it doesn't move together afterwards. So you have to understand that there is this thing called coefficient of restitution. Coefficient of restitution, where the E here. So yeah, I don't know whether you got this from the physics or from the high school physics, or I don't know, but it's V relative after divided V relative. So actually, if you find this on Google or on anything or on any course, it's going to write this kind of equation, which is, for me, it's annoying. I mean, it's correct, but it's just annoying. You don't know where the V2 is going, V1 prime is going, V2, V1 or anything. It's just annoying. It just annoys me because it's very unconceptual. It's just it just intrigues me to explain about this kind of way of thinking. So the E, the coefficient of restitution, it has to always be bigger or more than 0, where the 0 is the E0, it's fully inelastic or it moves together, so we don't really have to use E if it's 0. If it's 0, you don't need to use E. But the important part is when it's not 0. Usually if it's elastic, so if the problem tells you that the coefficient is elastic, when elastic, it's E equals to 1. Yeah, this is the important part, because sometimes they told you that the coefficient is elastic. Or actually this is the conservation of energy. And actually this E is actually derived from the conservation of energy. So E here is the comparison between relative velocity after and before the collision at the contact point. Okay, so it's contact point. The keyword here is relative and contact point. Okay, so if you just collide two things, right? So it has velocity v1 and it doesn't move. If you want, and this one is m1, this one is the mass m2. So from the momentum equation, it's going to be m1 v1 equals to m1 v1 prime added by m2 v2 prime. And from the energy, it's going to be half of m1 v1 squared equals to half of m1 v1 prime squared divided by half of m2 v2 prime squared. And if you want to solve this, it's going to be very rigorous. I mean, if you're not using calculator and if you're not given a number, you're going to solve this very rigorously, very hard. Not really lah. I mean, you move this, and then you equate stuff, and you use some math. You can do it, but it's just rigorous. So if you're using this coefficient of restitution instead, it's going to be far easier. So how to use the coefficient of restitution? So firstly, you'll get the use where the annoying one, it's going to make it easier, but it's still hard for me because you have that, okay, you just plug it into this equation and you have to memorize this. I mean, you can memorize this, but it's easier. It's the the relative velocity after divided by relative velocity before. It's very easy. Okay, to use my coefficient of restitution. It's not mine, but it's just the real definition. Like the concept of the coefficient of restitution itself is that, yeah, E equals to the relative velocity after divided by relative velocity before. So the first step is to define direction. Choose or decide. So obviously, because m2 initially is not moving, it's stationary, the relative velocity is v1 because v1 is closing in into m2. It's going closer to m2 with the velocity v1. So E is E1, let's say that it's elastic, right? Because it's the energy conserved, it's elastic, equals to the initial relative velocity has to be v1. But the final velocity, how? This is where you decide. define direction. So let's say after the collision, maybe the actuality is that it's moving this way and it's also moving this way again, but the velocity here decreases, let's say, or maybe this one moving but this one is not moving. But actually we just decide we don't care if our answer is negative, then our initial assumption is incorrect. So we just assume that the velocity here is going to v1 prime, and after the collision is v2 prime. Why? Because the relative velocity is going to be v1 prime added by v2 prime. How come? Because it's going away. They are both going away from each other, right? It's v1 prime added by v2 prime. So v1 prime added by v2 prime equals to m equals to v1. And now it's easy to solve, right? So then you have this first equation. The momentum equation will not change. This has to be the same, but this equation will be no, sorry. The momentum equation will also change. Sorry. Momentum equation based on your assumption. Because the assumption here, it's at first it's m1 v1. The initial momentum still is moving to the right, m1 v1. But after the collision, m2 v2 is going to the right, so it's m2 v2. But m1 v1 is going to the left, right? So it's negative m1 v1. It's prime, yeah. It's after the collision. For the momentum equation, if you're using this one, it's just assuming that after the collision, m1 will move to the right and m2 also move to the right. And then if it moves to the left, if m1 is moving to the left, v1 prime is going to be negative. But it's not very intuitive, because if you do this, you have to use this energy equation, or you have to use the equation regarding coefficient of restitution, but using this kind of annoying equation. But if you just assume from the start that direction both will going away, so the relative velocity has to be added. v1 is this, and then yeah, this is all the thing that you need to do, and then you just do some elimination from here and go on. And for this is there is no very significant difference if you either use this or the energy one, but it will make a significant difference when it comes to the rotation. So this is a problem that I saw from past year also. If you have this rod, okay, this rod, and you have this particle with mass m and velocity v, this rod is not attached to anything. It's just both of these is on top of a very slippery table. I mean, it's a slippery table, so there's no friction and stuff. And it has the mass m and the velocity l. So to do this kind of questions, you can first write down the momentum equation, okay? But I'll do this my way. First, we have to assume the direction. Choose the direction. When we choose the direction, I want that. So wait, this is the center of mass. This is the center, and it has the x from the center of mass. I remember. Yeah, there was numbers here, but no, I don't remember the number. But first we have to write down the momentum equation. Momentum equation. The momentum equation here is that it's mv equals to here after the collision, I want to decide where both of these goes. I will decide that after the collision, the particle moves to the left with the velocity v prime, and the rod will move to the right with the velocity v, the big v here, and the rotational angular velocity omega. Yeah. So momentum equation is going to say that it's negative m v prime, because After the collision, it's going to the left, negative mv prime, and it's added by big M times big V, because yeah, the mass of this rod is big M. Yeah, this is the momentum equation, the linear momentum. Its first equation, and second equation is the angular momentum. Angular momentum, where at first it's mvx because v and x is perpendicular. Okay, mvx, it's rotating clockwise, so I just say that clockwise is positive. And after the collision, it's going away with the velocity of v prime, so it's like almost moving like anti-clockwise, right? So it's negative mv prime x added by the angular momentum of this rod, which is 1/12 of ml squared omega. So notice that for this angular momentum, I use this center of mass as the reference point. Wait, there's a chat here. That question paper in the file of Telegram. Oh, okay. Sorry, I didn't notice. But yeah, I'm pretty sure that I got this correctly. I think yeah, we can just you can just check the number later on. This is the second question. Notice that I use the center of mass here as a reference point, because if we can here, there is no external force at all. There's no external moments at all. Thus, we can just choose any points for the angular momentum. But why I choose the center of mass? Because we know that the moment of inertia of this with respect to center of mass is 1/12 of ml squared. And if we want to use, for example, these points as a reference, we have to use another what to say, this moment of inertia, and because the thing is moving with the velocity v here, you have to use this concept of LCM added by L point mass, because after that you have the velocity of point mass here, right? But otherwise, we use this center of mass as a reference point. The L point mass will be 0, right? Because mvr, but the point mass r is 0, right? So yeah, whatever, it's easier. And the solution of these questions, the solution, right? The basic solution will just tell you to use energy, which is regress. You know, it's half mv squared equals to half mv prime squared added by half m big V squared added by half of I omega squared. Because for the rod, right, it has both the translational kinetical energy and rotational kinetical energy. And I have to tell you that for energy, kinetical energy for equals to kinetical energy translational one added by the kinetical energy rotational one. It exactly the same as the angular momentum one. They both have the center of mass one. This is the rotational one, and you have the point mass, which is the translational one. You have both. So if you have an object that has both rotational and translational, you have to add up both of the kinetical energy, which is here you have these 4 terms, which is crazy regress. I mean, you need to have those 4 terms, but it's just regress to use this, because it's all squared. Okay, this one is squared because it's on the second power. But we actually already have the this E here, this elastic. If it's elastic, it's gonna be 1. So the coefficient of restitution is very useful here because it's easier to understand. It's easier to work on. Is V relative prime over V relative. Notice that on the definition I use, the key points is relative and contact point. This contact point part is not even it doesn't matter if you use it on the one-dimensional problem like this, but if it's two-dimensional problem like this, it's important to notice that it's on the contact point. Where's the contact point? The contact point is on this part. This is the contact point. So at first, yeah, you obviously know E equals to 1. The initial relative velocity is V, right? Because it's just moving with the velocity V. This is the contact point. At first, it's closing in with the velocity V, but this is why the final velocity I make it to the left so that it's easier for us. Okay, we know that this is going to the right, and this is going to also further away from the particles here. So it has to be, so on the contact point we have to add, because the contact point here is moving to the right and the particle is moving to the left, so the relative velocity we just add it up, v prime added by the contact point velocity. So we just add up v prime added by contact point velocity. Oh, sorry, we just say it's vcp, where cp here is contact point. Okay, when we have this, we have to know how much is the velocity of the contact point. The contact point velocity is the velocity of the rod, but added with the factor of the omega here, because it's not only moving away with the velocity of the rod, but the rod is also moving here. They also move like this. It's moving here, but it's moving with as it rotates. So the rotation here matters. So as it rotates, it will move with this. Just imagine that it is moving both together like this. It's moving to the right. And this rotation, of course, adding up the velocity, right? Because it goes away to the right faster. The top part, right? I mean, the bottom part is going slower compared to this V. So because it has the omega here, and you have the distance here is x, right? So this point, if you don't have a velocity v here, it will have the velocity omega x. This one, if don't have big velocity. I mean, if you don't have a big velocity here, right? If you have an omega and a point is x distant away from the center, of course the velocity is omega x. It's omega r. It's the non-slip condition that I mentioned before. But because it also has the velocity v, it moves with omega x added by the center of mass velocity, which is omega x added by v. So the v contact point, VCP, is omega x added by big V. This is the small v. I have to say this is small v. So 1 equals to v prime added by omega x added by big V over v. So you have that big V added by omega x added by v prime equals to v. So this can replace our, so this is the third equation, but this is our better third equation, right? Because this equation is very rigorous, but this equation is very friendly to work on. So yeah, that's actually the coefficient of restitution. You can solve this yourself if you want. So 1, 2, and 3 here, and this is the alternative 3 that I want to use, that I use better. And you will get the exact same answer. Yeah. So yeah, that's about it for the coefficient and restitution, and that will end our meeting today. Wait, before that, you guys have any question for this coefficient of restitution? Is there any question? what if E is not zero? If E is not zero, it's partly elastic. If E is zero, it's inelastic where they move together. But when it's fully elastic, it's E equals to zero. But the question will not tell you that it's partly inelastic, because the question in physics, it's only telling you that, okay, the energy conserved, the energy, or they move together afterwards. If they move together, it's exactly zero. Exactly zero. If it's elastic, if they say that the energy conserved, it's elastic, it's going to be one, and in between is the real life problem. It's the real life problem. But maybe if someone that is explaining you, if someone is teaching you coefficient of restitution, they might test you that, oh, maybe the E is half, and then you just write down the E is half. E in between 0 and 1 is the real life problem kind of thing. Yeah, because in real life, right, it's not that like some part of the energy is not conserved. Any other question? This is a long meeting. Okay, if there's no other question, then this is our end of today's meeting. It is a very long one. It's 2.5 hours. Sorry guys if it's very long, but thank you for listening. Goodbye. Thank you also, New.